Hey friends, and welcome back to the channel. In today's video we're going to look at a very specific file format known as Digital Log Interchange Standard, or DLIS for short. If you have worked with well log data for some time, you will understand that there are a variety of file formats available, including LAS or LAS, LIS, CSV, and many others. So within this video we're going to see how we can use Python and a special library called DLIS.io to access a DLIS file and then view its contents and explore the metadata associated with that file and well. And we will take some well log measurements from that file and make a very simple plot from it. This video will allow you to get familiar with the basics of using DLIS.io, DLIS files and Python to access well log data. But first, let's take a look at what DLIS files actually are and how they compare to LAS files. Even though LAS files are probably one of the most common file formats for storing and transferring well log data, they have a flat file structure. This means that they have a series of columns representing well log measurements that have been measured against depth. LAS files are very simple to open in any text editor, and they can easily be modified if the need arises. DLIS files, on the other hand, are structured binary files that can contain multiple data tables. These data tables can contain information about the well, as well as the logging curves. One of the big benefits of DLIS files is that they can store multi-dimensional and highly sampled data. And this can include acoustic waveform data, NMR data, and borehole image logs. DLIS files can also store information about multiple logging passes and multiple runs, which is different compared to simple LAS files. DLIS files were developed in the 1980s as a way to store well log data in a structured format, and the format was then subsequently published in 1991 by the American Petroleum Institute. So rather than go into the specific details of the structure behind DLIS files, you can find a link down in the description below which will take you to the DLIS standard, and you can see an example of that here on screen. Anyone who has worked with DLIS files knows that they can be very awkward to work with, and it's not easy to access the data that is stored within them. As a result, you need some proprietary software to access those files and view their contents. So to combat this, there are a number of open source libraries that have been developed in Python to easily read and access the data stored within the DLIS format. And the most popular library is the DLIS.io library, which has been developed and maintained by Equinor, and it allows users to easily load DLIS files and access the contents and extract that data into a more meaningful format such as a Pandas data frame or into individual lists or arrays. And it also removes the need for understanding the DLIS structure. You need to have a basic understanding of what frames are, what channels are, and then you can access them very easily with the syntax that is provided by this library. And it is the DLIS.io library that we're going to focus on for this particular tutorial. We're going to see how we can load in DLIS files, explore the contents and the header information, as well as the curves. And we will see how to make a very simple plot using some curves that are contained within that DLIS file. So let's go over to our Jupyter Notebook and see how we can do this. Now that we are in our Jupyter Notebook, the first step with any of our projects is to import the libraries that we're going to be working with. So for this particular exercise, we're going to be loading in DLIS.io as DLIS, and this will be used to import our DLIS files. We will be using Pandas, which is imported as PD, to view the data as a data frame. And we will be importing matplotlib.pyplot as PLT to view a visualization of our data. And finally, at the end of this cell here, we're setting an option called display.maxRows to 500. As we're going to be working with very large data frames, this option here allows data frames to extend to 500 rows, compared to normally where you would only see the first few rows of a data frame and then the last few rows of a data frame. So this allows us to display all that data in a single data frame. So let us run this. Next cell, I'm just importing DLIS.io and calling upon the version just for reference if you're watching this at a future date, so you know which version I am working on, as this library is continuously being worked on and developed. So now that our libraries have been imported, we now need to load in our data, and the data we are using comes from the Dutch sector of the North Sea. And within this DLIS file there are many different types of data sets, including borehole image and acoustic waveform processing. But for this particular tutorial we're going to keep it very simple, and we're just going to focus on loading and accessing the parameters of the DLIS file, as well as some basic logging curves. So to load in our file, we need to set up two variables. First one is f, and then the next one is *tail. And The reason for this is a DLIS file can contain multiple logical files. Therefore, using this syntax allows us to output the first file to F, and then any subsequent logical files are placed into the tail variable. We then set this equal to DLIS.load, and then we pass in the location of our file. So I have this file that is located within the data subdirectory of this project, and you can find this on my GitHub repo if you want to follow along. So let's load this file in, and we can start to have a look at what is within our data. We can call upon print f, and we can see that we've got our logical file loaded in. And if we want to just have a look at the tail, just to be sure, we can then call upon tail, and we can see that there is nothing within that list. So that means that we don't have additional logical files within this particular DLIS file. So there are a number of methods that are available when you look at the logical file. So if I call upon f followed by dot, and then pressing on the tab key in Jupyter Notebook, we can see that there are a number of methods and attributes that tied onto this file object. We can see frames, groups, measurements, messages, etc. So if I just call upon f.channels, we can see all of the logging curves that are present within this file. And what we get back is quite a long list. So it can be very hard to see what we've actually got in here. And further on in this tutorial, we'll see how we can make this into a nicer looking data frame. So one simple method that we can call upon is f.describe. So when we run this, what we get back is a description of that logical file. We get an indication of how many frames are within that file, and then how many channels are within that file. So the channels typically represent logging curves, and frames are representative of multiple or different logging passes or different runs of data. So we know we've got 4 different passes or 4 different runs of data in here, and we have 484 curves for all of that. We can then see that we've got different objects in here. We've got a file header, we've got the origin, we've got an equipment list, we've got a tool list, parameters, and many other different things down here that you can explore. So when working with DLIS files, we need to understand where the data has come from. What is the origin of that data? So when we call upon the origin method on the file, we can then see where that data is sourced from, and we can have multiple sources, so we need to account for this by unpacking the origins into 2 variables. And we can do this as we did before, where we call upon origin, and then followed by a star, and then origin tail. And we then set that to f.origins, and then we can run that. So I will add an extra cell here, and we can call upon the origin. So let's have a look at that. So we've got something in that, but do we have anything in the tail? No, so there's no extra origins within this data set. Similar to the f.describe method, we can then call upon origin.describe. And this returns a nice formatted piece of text that tells us about the origin of that data. We can see that it was recorded for a company called Wintershall, and it was produced by Schlumberger, and the date of that was back in 2002, almost 20 years ago. And then we can see what other services were used within this particular file, or within this particular well. We can see that we've got microelectrical scanner, we've got DTS telemetry cartridge, and we've got a dipole shear imager, so we've got a lot of data that has been recorded for this well. Not necessarily within this particular file, but we know that if we go to the nlog database, we can access the other files from this well and view the data that is contained within that particular well. So now that we understand where our file has come from, we can then move on to actually looking at the data. The next step is to look at the frames, and the frames are representative of different logging passes or different stages of data. So we may have raw well logging measurements that have been acquired during the main logging process, and then we may have petrophysical interpretations or even processed data. So to have a look at the different frames within this data set, we could call upon f.frames, and we can see that we've got frame 60b, frame 10b, frame 1b, and frame 15b. Now that makes no sense at all to me, and probably not to you, so we don't know what these frames represent. So what we can do is we can start to build up a picture of what is contained within each of these frames. We create a for loop for frame in f.frames. So now we're going to loop through each of these frames, so frame 60b, 10b, 1b, etc. I will loop over the channel, so we can go for channel in frame.channels, and then if the channel.name is equal to frame.index, then we're going to take the units for that particular frame. So we may have that recorded in inches, meters, feet, and what we can do is grab the units for that particular index. We can create a variable called depth_units is equal to channel.units. Now I've already typed out the part below where we're going to be printing different parts. So I'll go through each of these. So the first part is calling upon the frame name. And this is calling upon this part here within the frame, 60B, 10B, 1B or 15B. And then we're going to call upon the index type, so we'll know whether it's been measured in depth or whether it's been measured in time. We can then grab the depth interval that the data has been recorded over, so we're calling upon the frame.index min and then index max. So this is our minimum depth and our maximum depth, or minimum time and maximum time if we're working with time-based data. And this is where the depth units comes in. We've created it up here, and we're now passing it in here at the end. And all of these are F strings, or formatted strings. So we put an F at the beginning, and then with curly braces we can then pass in the individual parameters or the individual variables. So next we are grabbing the spacing, or the interval between each depth measurement, and we're appending the depth units to the end of that. And then we're just calling upon the number of channels that are present within each of these frames, as well as the channel names. So the channel names are our individual logging curves. And then this /n/n is just putting in 2 new blank lines at the end of this text string. So when we call upon this and run it, it may just take a few seconds to run, but what we get back is a nice summary of our data. We can see we've got the frame name 60B, and we've got more information here. So we know it's been measured in depth, we know the depth interval and the spacing here. So the depth interval hasn't come through correctly, as it may not be set within the file, and that can happen occasionally. And then we have 77 channels within this particular frame, and then we have our depth channel, and then we have bit size, cable speed, tension, elapsed time, deviation, etc., and some of our acoustic waveform data, or some of our acoustic curves, DT4P and DT4S. So we know this is our main data frame that contains the majority of the data. If we go down, we can see 10B contains depth and 3 other curves here. We've got ID, WD, time and SCD. So at the moment we don't know what some of these mnemonics are, but we will see how we can grab a data frame of each of the channels within the file. So as seen earlier within the DLIS file, we have seen that we've got a number of different objects associated with our file. So to make it easier to read rather than doing simple print statements, what I've got here is a simple function that creates a simple data frame, and what we pass in is the parameters or even the channel names into this, and we get back a nice data frame. So we can see that we're creating an empty data frame to start with, and then we're passing in this special argument called quargs, or keyword arguments. So there are multiple of these, which is indicated by the double asterisks. And then we're going to loop through the key and the value within these particular keyword arguments, and then we're going to append it to a list of values, and then we get the item and the key for that. And this will make sense when we go into running this particular function. I'll run the cell so that we've got that function ready to go, and now we can access it here. So let's have a look at our parameters. We can create a simple data frame. param_df is equal to summary_data frame. So I will call upon here, I'll call upon the brackets and pass in f.parameters, and that is our object. So within that object we're going to be looking for the name, and that is going to be equal to name. And then long_name is equal to long name. And then we're also going to call upon values, which is equal to values. So when working with DLIS files, we can have people's names within the file, and this can be problematic when you are publishing the data or publishing the notebooks to say GitHub, and those names are in view, and then they can be picked up by search engines. So to hide the names and protect people's privacy, what I've done here is put in a little mask into our data frame. So we're going to be looking for key parameter names here called R8, RR1, witness, and then engineer. And this just hides the names from the output. If you want to display the names, then you can remove this, but I would recommend against uploading that data afterwards, just to maintain people's privacy. And then at the end, we're calling upon our param_df to get our data frame. And what we get back is a nicer looking representation compared to what we have up here, where we're just running with print statements. So now we're looking at the specific parameters. We can see that we've got A, C, 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 which is our accelerometer coefficients. If we can scroll down this, we can see what the bit size was, which is 5 3/4, what the borehole salinity was, and the casing grade, if that's been recorded. So we've got a number of different processing parameters for our acoustic tool. So we've got our delta T fluid, our delta T matrix, if we need to call upon them. So the next part we're going to look at is channels. And channels within a frame are the individual curves or array data. And we can view a quick summary of these in the same way that we did with the parameters. And we can just create a variable called channels, and that is going to be equal to the summary data frame, and then we just pass in f.channels. The name is equal to name, long_name is equal to long name, and values is equal to values. And then we can call upon the channels and we get back a nice data frame. So where we were above, or where we were looking at the channels above, we can see all these different mnemonics. And if you're not familiar with some of them, like I am, so some of them I do recognize here or within the acoustic tools. We've got this data frame here where we can go and have a look at some of these. So we can see that we've got BA11, which is our calibrated data buttons for, our image tool. And then we have bond index, we have our STC peak coherence, C1R1, and we can scroll down and have a look at all the different mnemonics within here. We can repeat this process with the tools. So what we're going to do is create a new variable called tools is equal to summary data frame, and then we pass in f.tools. And then name is equal to name. And this is where it changes slightly, so we're going to be calling upon the description, and that is going to be equal to description. And when we call upon the tools, we get back a very simple data frame. We can see what the different tools are within this particular file. We have a DSSTB, which is our dipole shear imager, and then we have our telemetry and tool bus adapter, and we also have a microelectrical scanner and a gamma ray tool. Just to illustrate, if we just called upon f.tools, we end up with this list here, which is not very useful, same as what we had with the frames. So for this particular example, we're going to be working with the DSSTB tool. So we need to know what parameters are contained within that particular tool, and we can do that by setting the object. So we'll call upon DSSTB is equal to f.object, and with this function, with this object function, what we're going to do is grab the type of object that we're wanting. So for this particular example, we're going to be calling upon the tool type of object. We're going to be calling upon the DSSTB tool, and then we're going to grab the parameters, the same as we've done before. We'll call upon DSSTB underscore params is equal to summary data frame, and then we pass in DSSTB dot parameters, and then we'll set the name is equal to name, and then again back to the long name, so that we've got the more descriptive name of that particular mnemonic, and then we need to call upon the value, which is equal to values. So now we've created that, we need to call upon that new parameter data frame, and we can do that by calling upon DSSTB underscore params Now we've got our individual parameters for the DSSTB tool. We've got our borehole status, borehole temperature, and we can see some of the processing parameters as well. Now that we have looked over the metadata of the well, such as the well name, the well header information, the curve information, as well as the parameters, we can now start to access the data that is stored within the file. So frame1 is equal to f.object, and what we're going to do is we're going to grab the frame, and we need to know which frame we're going to be calling. If we go back up to our frames, we can see that the majority of the data is stored within frame 60b. And this is a frame that we're going to be working with. What we do is we pass in the second argument here, which will be 60b. And if we call upon frame 1, we can see that we've got frame 60b. So we know we've got the right frame. So now that we've seen how to access the frames, we can access the channels. And we can do this just by passing in channel as the object that we are wanting to grab. And then we're passing in the actual name of the channel that we want to also grab from the data. And with these print statements, what I'm doing is just grabbing the name, the long name, the units, and the dimension. So if the dimension is greater than 1, then we know that we're dealing with an array. So here we see we've got PWF4, which is a packed waveform data for the monopole P and S. And we can see that we don't have any units with this, but we do have a dimension of 8 by 512. So with these acoustic tools, we know that we've got 8 receivers within that acoustic waveform. And then within each of these waveforms, we have 512 measurements. So we're not going to plot the waveform data, but we are going to plot the individual logging curves. And we can simply do this by creating an object from our frames1 that we created above. Curves is equal to frame1.curves. If we call upon that, we've now created a curves object. And if we want to have a look at that, we can call upon curves, and we can see that we've got a mass of data here, and we don't know which logging curves this belongs to. So what we need to start doing is actually grabbing specific curves from this array. And we can do that by assigning a few variables. So let's assign depth is equal to curves, and then we're calling upon tdepth, which is our depth. And as the depth within this particular file is measured at 0.1 of an inch, we need to convert that to meters simply by multiplying by 0.00254. And then we can call upon DTCO, which is the curve that we're going to be wanting, and we're accessing this like a dictionary. So we're calling upon DTCO, and then DTSM, which is our shear slowness measurement curves, and then DTSM. And what we can do is call upon DTCO. What happens is we get back an array. Same with DTSM, we get back an array. And we can see that we've already got our shear slowness values and our compressional slowness values. So to make sure that we've got the data that we're wanting and that it makes sense, we can create a simple plot by calling upon plt.plot, passing in depth for our x-axis, and then DTCO for our y-axis, and then also plt.plot, depth, and DTSM, as these two curves usually go together. Okay. plt.ylim is equal to 40 to 240. And when we run that, we can see that we've got a simple log plot back, we've got our depth measurement on the x-axis, and we can see that we've got our compressional and our shear curve. So DLIS.io is just one of the few libraries that are available for reading DLIS files. It's probably the most popular library, but there is also a library called DLIS.py. And you can see here from the GitHub repository that it's not really been maintained for the past 3 years. However, it is still worth checking out and trying it out on some DLIS files to see whether it works with your data. However, DLIS.io is actively maintained and updated by Equinor, as you can see here from their repository on GitHub. Let me know down in the comments below if you've used either of these libraries. With that being said, I hope you've enjoyed today's video and found it useful. If you have, make sure you give it a like down below, and if you want to see more content from this channel, click on that subscribe button and ding that notification bell. So thanks for watching, and until next time, bye for now.